Okay, so welcome back to our second lecture by Dick Canary about Sullivan's Dictionary. And here we go.
Okay, thanks. So I'm just continuing on. Today I'm going to be the setup man for Dave Gabai, who's going to be talking about his proof of the tameness conjecture. So just to remind you, we talked briefly about the tameness conjecture during yesterday's talk, but it predicts that if you have a hyperbolic three-manifold and its fundamental group is finally generated, then it should be topologically tame, which means it should be obtained just from a compact three-manifold by throwing the boundary away. This is sort of how we think, how we at least first think that a open three-manifold might arise. It's not true in general that all open three-manifolds are like this, though. I thought about doing an example, but Misha asked me to talk about Hausdorff dimensions, so I'm going to do that instead. So a first topological object, which is sort of a replacement for tameness in a lot of settings, is something called the compact core. So if you have this hyperbolic three-manifold, say, then always sitting inside there, it's a theorem of Peter Scott's, that there's some compact submanifold which carries the fundamental group. So the inclusion map is a homotopy equivalence. And sort of what you're thinking now is great. The complement here should have a product structure. If this is F, then this guy should be just F cross the half line. And if it were topologically tame, I could always choose a compact core which had that property. So this sort of is a first approximation to tameness. And so what we're going to do is sort of analyze the ends. So the ends here, and you can take sort of some abstract definition as a direct limit of complements of compact sets and blah, blah, blah. But we're just going to think of an end as a component of the complement of a compact core. So if you were being formal, that would just be some neighborhood of an end. So this picture has three ends, and we're going to want to prove that they're topologically products. Well, you're going to see that in the next talk. But also what we're going to want to do is, what I'm going to do in a lot of this talk is talk about applications of the tameness conjecture. And at first it would seem pretty surprising that this topological conjecture would have any sort of geometric consequences. But what we're going to see is that once we know it's topologically tame, we're going to know a lot about the geometric structure of these ends. So the first part of the talk, we're going to talk about what do the ends of a hyperbolic three-manifold look like geometrically. Okay. So again, I'm going to make some simplifying assumptions to make my life easier. If I don't say it, the fundamental group is finally generated, and it contains no parabolic elements. So another way of saying that is the hyperbolic manifold has no cusps. If you want to think about it picturesquely, if you wrap a rubber band around something in your manifold and you let it loose, it will pull tight around a closed geodesic. It will not go zinging off to infinity like it would if you wrapped it around a cuspidal curve. So in this situation, Allforce finiteness theorem tells us that the conformal boundary is a finite collection of closed surfaces. Remember, the conformal boundary is somehow sitting it out here at infinity, being a conformal boardification. So, of course, the nicest thing would be if, remember we saw that if you're convex co-compact, that means this conformal boardification is you have one of these out each end. But we don't always have that. Okay. So a geometric object we want to talk about here first is the convex core, and that's just going to be the smallest convex submanifold which carries the fundamental group. So in this picture here, there's the compact core. But the convex core might look something like this. It's going to be a convex submanifold, and maybe it sort of blocks off these two ends, but then it contains that entire end. Okay? And if you want to think about it explicitly, and this is sort of an abstract definition, is the smallest convex submanifold, you can just take the limit set of your group, you take the convex hull of that limit set within H3, and then you take the quotient by the group. That's going to give you the convex hull. And one observation due to Thurston is that the intrinsic metric on the boundary is hyperbolic. Moreover, he says it's a pleated surface because it's made up from a bunch of pieces of planes bent along a bunch of lines. Well, so it may be, a Cantor set's worth of lines you bent along, but if you think about if you're away from a vertex, the local metric on a polyhedron or any convex set in Euclidean space will be Euclidean if you're away from sort of a vertex point. And this is really that same observation in hyperbolic space. And the convex hull, all the vertices are at infinity, so all the places where you might worry about the intrinsic metric on your polyhedron being bad aren't there.
Yeah. Is it obvious why it's not compact, the convex?
Excuse me?
Is it obvious why it's there? It cannot not be, it's not compact necessarily.
Well, the limit set lies out in infinity. So, yeah.
So I think he's really asking something that was a theorem in the 60s. Why do these degenerate groups exist? Why aren't they always geometrically finite?
Oh, yeah, I'll give you an example. I will give you an example of that. That's 2 slides in.
The Fuchsian groups, this doesn't happen.
Right. Yeah. Good point. Okay, I was misunderstanding the question. Thanks. Okay. So let's talk a little bit about the geometry of the complement of the convex core. Well, this is a convex set. Well, so if you take a convex set, if you look at the complement, you take any point in the complement, you can sort of take the nearest point projection down to the convex set. And what is that going to give you? That gives you sort of and you get an entire line's worth. So you see that if you're in the complement of the convex core, this projecting onto the nearest point, this idea just gives you a product structure on the complement. Okay? And so we can see that the complement is just a product. And so, there's these vertices points. So there might be a whole wedge of lines coming into one point, but that's not going to affect topology. So the complement has a product structure. That's good. And moreover, you can sort of look exactly what the metric looks like. Locally, it looks a lot like you project onto a plane. If you take a hyperbolic plane, you take the coordinates, which are given by the distance. The point you project to is one coordinate, and the distance to the plane is the other. The metric is exactly cos squared t ds squared, where ds squared is the metric on the plane, plus dt squared. And what it turns out is that, well, you've taken your plane, it's a little bent, so you don't exactly get that metric, but you get a metric which is by Lipschitz to that metric. Okay? And so another thing you see here is that you can see here, it's not too hard, I'm not really going to prove it, is that this sort of product structure extends out to into infinity. So you can make all these rays sort of end on the conformal boundary. So that, in fact, the conformal boundary and the boundary of the convex core are homeomorphic, and, in fact, that this convex core is just up to homeomorphism, just the same as the conformal morphification. Okay? So if N is convex co-compact, you get this incredibly nice picture for the geometry. So you would have this compact submanifold, and outside the convex submanifold, you have this product structure, and in this product structure, the metric is exponentially expanding. Right? This is how we expect hyperbolic space to be, and this is how it is in the convex co-compact case. Okay. So we're not really going to use this here, but I thought, this is another great theorem of Dennis's, so it's worth mentioning, is that there's a relationship between the metric on the conformal boundary, the Poincare metric on the conformal boundary, and the metric on the boundary of the convex core. Well, actually, the first version is in terms of the conformal structure. They're uniform if you assume that each component of the domain of discontinuity is simply connected. Then, for example, in the quasi-Fuchsian case, then the conformal boundary and the boundary of the convex core are uniformly quasiconformal. So this allows you to translate geometry, which is really happening in the Riemann sphere, to geometry happening inside your Riemannian three-manifold. So, I mean, it's sort of, there was an earlier result of Bers which said that if you had a bound on the length in the conformal boundary, you would get a bound on the length of the corresponding geodesic in the hyperbolic three-manifold, but this is a much more precise relationship. So there's a little history here. Epstein, Marden, and Markovitch showed that the best constant is somewhere between 2 and 14. And in fact, it had been a question of Thurston's, well, would 2 work? And if you sort of think about it, in the most obvious examples you do, 2 always works. But they were able to come up with a very clever example where 2 doesn't work. And then you might ask yourself, well, gosh, what if the boundary isn't simply connected? Well, then it turns out that they're still quasiconformal, but now the quasiconformal constant depends on the injectivity radius of the domain of discontinuity. So if you have a short geodesic in the domain of discontinuity, then this quasiconformal constant is going to be large. Another way of saying that is if you have a large modulus annulus in the domain of discontinuity, then this quasiconformal constant is going to be large. And if you have a quasiconformal map with bounded constants, you can turn that into a bi-Lipschitz map with bounded bi-Lipschitz constants. So you can either talk about conformal structures, or you can sort of go and talk about hyperbolic structures, whichever you prefer to talk about. So let me give you sort of my version of the idea why this is true. So suppose this is some component of your data discontinuity. It's simply connected. The most basic thing you know about the Poincare metric is it's really comparable. It's 4 by Lipschitz, or is it 2? I forget. To 1 over distance to the boundary. So the metric is like a lot like 1 over d. On the other hand, if you go up and you take the ball of radius 1 over d, it's a hemisphere which is in the complement of the convex core, and it's at height exactly d. So therefore, at that point, at the top, sort of the metric is being scaled by 1 over d. So sort of the same factor. And it also explains why, when you have these annuli, they're due to Baron and Pomeranke, you know that as you have larger and larger modulus annuli, the relationship to the 1 over d metric deteriorates. So there's sort of very good complex analytic reason why these things should work. Okay. Okay. So here, sort of an obvious definition. You're in the nicest case if one of these ends is just the complement of the convex. If one of these ends is just a component of the complement of the convex core, then it has a product structure, so it's topologically tame. That end's all taken care of. We understand its geometry. We understand its topology. Everything's great. And we say a manifold is convex co-compact if every end is geometrically finite. There's a little oddness in the definitions here, because the definitions are done in the case where you're allowing parabolics. So it makes the terminology seem a little weird. Okay, so how about a geometrically infinite hyperbolic three-manifold? And I think it took a long time before people could figure out how you make these. And in fact, in the late 60s, Leon Greenberg was the first person to show that there even exists a hyperbolic three-manifold without cusps, which isn't convex co-compact. And I'm going to sort of, he actually showed just plain existence. Jorgensen was the first one to actually exhibit a group. And so I'm going to take a little bit of a cheater's viewpoint here. So I'm going to use a fact due to Thurston, which is if you take a three-manifold which fibers over the circle, which just means that three-manifold fibers over a circle is just the mapping torus of a homeomorphism of the surface. So you just glue by some map phi. And Thurston showed that if you take a typical phi, that mapping torus will in fact be hyperbolic. So in fact, if phi is pseudo-Nosov, that mapping torus is hyperbolic. Okay, and this also follows from Perelman's work now. And there's a natural cover of this, which is, here's the fiber subgroup. Take the cover associated with the fiber subgroup. What does the cover look like? Well, you can imagine this being made from a Lego block and you glue the top to the bottom, the cover is made by you unglue and you take infinitely many copies of that Lego block and stack them one on top of the other on top of the other. So here's one, there's another, there's another. So there's all these Lego blocks, and when you go up, you sort of take the point xt goes upstairs to the point phi of x t plus 1. This is in fact a regular cover, and it admits a periodic action by z. Okay. Okay. So why isn't that convex co-compact? Well, if I take a curve in the homotopy class of, I take a curve in the homotopy class of the surface here, say that's alpha, I'm going to pull it tight, I'm going to find a geodesic there. Now what's the preimage of that up in that cover? Well, I have geodesics going, and I have a geodesic in each and every one of these blocks. So they go all the way up to infinity and all the way down to minus infinity, and the convex core contains all these geodesics, right? Because it's upstairs is the convex hull of the limit set, so it's up in the universal cover. It contains the axis of that corresponding isometry. So right away, the convex core cannot be compact. And in fact, if you notice that I told you that Allforce finiteness theorem told you that the boundary of the convex core is compact, since it's just homeomorphic to the conformal boundary, well, really, there's no way to stick a compact thing in here which doesn't, I can't find a compact boundary component so that all the geodesics are to one side of it. So in fact, the convex core must be everything. Okay. So there's a sort of a story which I got confirmed at lunch today as having been heard from the master's mouth, which is that someone initially asked Thurston, well, what three manifolds might be hyperbolic, back before he had a geometrization conjecture. And he said, well, of course, these three manifolds for a circle couldn't be hyperbolic, right? Because if they were hyperbolic, then you would have a cover like this, and this cover grows linearly, right? So if there's one third thing the word hyperbolic means is that the volume is that everything should grow exponentially or decay exponentially. And then he also said a more sophisticated thing, which is suppose you take a minimal surface here in the homotopy class of the fiber. Then if you look at the preimage of that minimal surface, you see infinitely many copies of those minimal surfaces. Those minimal surfaces have curvature less than or equal to -1. Okay? And so if you think of what happens, but they're a bounded distance from another. So if you look up in H3, that gives you a bunch of parallel minimal surfaces in H3 separated by a bounded distance. Sounds pretty improbable on the face of things. But anyway, turns out they exist. Okay? And so this example is also supposed to motivate the definition of simply degenerate. So we're going to say an end is simply degenerate if it's homeomorphic. First of all, I'm going to put the topological tameness right in the definition of simply degenerate. And then you're going to require that going out the end, so this is an end which is f cross the half line, and then going out the end, there's a bunch of these surfaces. So this is hn of f. And the key thing is that the intrinsic metric, or the pullback metric on that surface, should have curvature less than -1, perhaps in some singular sense. And each of these surfaces, when I draw that picture, you just assumed that they were level surfaces in the product structure. So they should be level surfaces within the product structure. And to be a little more technical, they should be homotopic to level surfaces within the end. By homotopy, I can't take the surface, homotop it, mix it up inside the manifold, come back out, and get a level surface. And they also, as the picture suggests, they should go marching out the end. So in this case, a perfectly good surface would be you take this minimal surface in the homotopy class of the fiber, and you would take the preimages of that minimal surface, and they go marching out this end and marching out that end. Okay? And sort of the magic of Thurston, he somehow figured out that every geometrically infinite end should have such surfaces, and that this is the key property. So, I mean, you sort of looked at it, even looking at it in retrospect, I don't really see why you would think that necessarily. So it's pretty impressive. So we're going to say a manifold is geometrically tame if and only if the ends are this one of two types. Either they're convex co-compact, which means they have this exponentially flaring end, or they're simply degenerate, which means that we have these surfaces going out the end. These are sort of very contrasting situations. Notice if you take a surface that's sort of far out this end, then the area of that surface is going to infinity. And its curvature is going to 0, no matter what you do. So there's sort of no middle ground here between the two. The two ends behave very, very differently. And with the definition I gave, it's clear that geometric tameness implies topological tameness, because geometrically finite ends are tame for a pretty simple reason, and simply degenerate ends are tame by definition. So in a matter of fact, Thurston gave a weaker definition of geometric tameness, and then he actually was able to prove that implied topological tameness, but his definition only works when you assume the group is freely indecomposable. It won't, you can't do things like prove Allforce measure conjecture with his original definition in the general setting. But he was only working in the freely indecomposable setting. So it turns out that topological tameness is equivalent to geometric tameness, and it's really the geometric tameness which is used to obtain the geometric and dynamical and analytical applications of the tameness conjecture. Okay, so let me give you a little history here. I mean, first of all, Thurston defined the idea, and then he showed that many limits of freely indecomposable convex co-compact Kleinian groups are geometrically tame. And this is basically he proved that enough of them are geometrically tame for use in his proof of his geometrization theorem. And this is sort of why he developed this technology. And then Bonahone later built on the work of Thurston to show that every hyperbolic 3-manifold with finally generated freely indecomposable fundamental group is geometrically tame, and hence topologically tame. And then I showed that geometric tameness and topological tameness are the same thing. So let me just show you the idea because it's kind of quick. So the idea here of why topological tameness implies geometric tameness relies on Bonahone's result, which is that if you have this sort of topologically tame manifold, and it doesn't have freely indecomposable fundamental group, which means that if you look at this some compact core, then there's some curve in the boundary that is homotopically trivial in the 3-manifold, but not in the surface. So what you do is you take a super complicated curve in the middle here, and you form the double branch cover over that super complicated curve. And topologically, that manifold will have freely indecomposable fundamental group. And then you can use a little trick of Gromov and Thurston to desingularize the metric. The metric upstairs, when you're in the double cover, will have a singularity of cone angle 4 pi. So you can either just work with that, or you can sort of deform it in a regular neighborhood to make it actually just a negligibly curved metric. So really, this theorem is very much built on Bonohone's theorem, but it also has some uses even today, because it means if you have a hyperbolic three-manifold, you're trying to work with its end, you can always just sort of assume the end the word is incompressible. So if you have this end here, and maybe there's some curve in the boundary, and it bounds a disk in the three-manifold, I can just pass up to the cover, and I have in the cover manifold, that end will no longer, this curve will no longer bound a disk. And this sort of is sort of a useful little trick, because it's often easier to work in that setting. Then we went along, you can prove that strong limits of topologically tame hyperbolic three-manifolds are topologically tame. That means you take a sequence of limits and they converge algebraically, and if you look at the associated manifolds, they converge geometrically in the sense of Gromov, meaning that if you look at an R ball in the limit manifold, and then you look far enough along in the sequence, it looks just like the R ball in the approximates. Then there were a bunch of results which eventually terminated in a result of Brock and Soto, showing that all limits of convex co-compact hyperbolic three-manifolds are topologically tame. There's a result of Soto, which I think was sort of influential in the final solution of the Tameness conjecture. He showed that if a hyperbolic three-manifold can be exhausted by compact cores, then it is topologically tame. And finally, separately, Agol and Caligari-Gabai gave proofs of the entire conjecture, and Soma sort of gave a nice proof which combines ideas from both of them. Okay, so I'm not going to really say anything at all about the proof, because that's what Dave's going to do next. But what I want to do is move on and talk about some of the consequences of the proof, and probably the most famous consequence of the proof is the so-called Allforce measure conjecture. So this predicts that if you have a finely generated Kleinian group, its limit set is either everything, the entire Riemann sphere, or has measure 0. And if it's the entire Riemann sphere, then the group acts ergodically. So as we mentioned yesterday, Dennis proved in his rigidity theorem sort of all the consequences of this, but not this actual statement. So this does actually follow from the Tameness conjecture. Well, I mean, I'm not sure all the consequences, but a lot of the consequences that we think are most important. And Allforce proved this conjecture for convex co-compact Kleinian groups, and I'm about to sketch that proof for you. It's a really cool proof, and it also generalizes to prove the theorem for geometrically tame hyperbolic three-manifolds. So to give a nod back to the dictionary, the area of the Julia set of a hyperbolic rational map is 0. But as Misha mentioned, it's not true that the area of a Julia set of a general rational map is 0. And in fact, there's examples of quadratic maps where the area of the Julia set is positive. Okay. So how did Allforce's proof go? Well, turns out it's an application of the maximum principle for harmonic functions. So first of all, how do you define a harmonic function? Well, we first define it up in the universal cover, up in H3, and then we do it in such a way that definition is equivariant, and it's going to descend to a harmonic function on the manifold. So how is it defined in H3? Well, you think of the sort of limit set as out in the nighttime sky. And the limit set is, well, it's either the stars or the darkness, depending on your viewpoint. But you look out into the nighttime sky at the point you're standing at, and you say, how much of my sky consists of limit set? What proportion of my sky consists of limit set? And that's going to depend as you move some points. So for instance, if you had a Kleinian group where the limit set was the upper hemisphere, as you walked up towards the North Pole, this function would converge to 1, and as you worked towards the South Pole, this would converge to 0. Okay? And then there's it's not particularly useful, but there's a formula for it. And one thing you notice is that if you're outside the convex hull of the limit set, so here maybe you're here. Let's draw a two-dimensional picture. So the limit set looks something like that. There's the convex hull limit set. You're standing out here. That means there's an entire half plane through you which separates you from the convex hull. So if you look anywhere that way, if you look anywhere in the direction to the outer hemisphere bounded by this support plane, you don't see any limit set. So the limit set takes up less than half of your nighttime sky if you're outside the convex hull. So, okay, outside of the convex hull is less than 1/2. There we go. On the other hand, the limit set is invariant under the group. Therefore, my definition is invariant under the group. So H descends to a function, harmonic function defined on the quotient hyperbolic manifold, and it's less than 1/2 off of the convex core. But a harmonic function achieves its maximum value on over a compact manifold on its boundary. So if it's less than 1/2 on the boundary of the convex core, and the convex core is compact, it's less than 1/2 on the convex core, which means it's less than 1/2 everywhere. So you lift it back up to the universal cover, it's less than 1/2 everywhere on H3. Okay, that says no matter where I stand, the limit set takes up less than half of the nighttime sky. But, if a set has positive measure, it has to have a point of density, which means that there's some point where if you look at it on finer scale, that set is taking up a bigger proportion of the little ball. And so if you start walking towards a point of density, you're sort of walking towards it, the nighttime sky will start being filled by limit set, so that this function will have to converge to 1. Well, it can't converge to 1. It's less than 1/2. Therefore, there can't be any points of density. Therefore, the limit set must have measure 0. Okay, so really, this is a really great proof. And so if you notice here, what did this have to do with convex cocompactness? Convex cocompactness only came in applying the maximum principle on a compact submanifold. So all I have to show is that if I take a harmonic function on a topologically tame hyperbolic 3-manifold, it achieves its maximum over the convex core on the boundary. Because it's still true that off of the convex core it's less than 1/2, and so on the boundary of the convex core it's less than or equal to 1/2, which means that if I knew this, then I would knew it was less than 1/2 everywhere, the whole proof would go through. Okay? What? Yeah, okay. You also have to show that if like in this case here, if the convex core has no boundary, then you have to show it admits no non-constant harmonic functions. That's what you have to show. And that, well, if the convex core has no boundary, the limit set is the Riemann sphere. To show that in the case the limit set is the Riemann sphere, that the action of the group is ergodic, you show that there are no non-constant harmonic functions. Yeah. But I'm sort of ignoring the ergodicity part. Okay, so Thurston, this is really sort of an argument of Thurston's, although he only worked in the freely decomposable case, so you had to work out what the definition should be. You have to generalize it a little bit, but if this is really due to Thurston, says that if your manifold is topologically tame, and you take some positive superharmonic function on your manifold, that means the divergence of the gradient of the function is less than 0, which means that if you flow in the direction of greatest increase, the volume is non-increasing. But if you flow in the direction of greatest decrease, then the volume will be non-decreasing. Okay, that's how you want to think about it. And then I actually did catch this little thing on the third time I went through, that in fact, if the convex core is everything, you want to show that there are in fact no positive superharmonic functions. So this will be enough to show that the Allforce measure conjecture holds for topologically tame hyperbolic 3 manifolds, and hence for all finally generated Kleinian groups now that we know Marden's tameness conjecture. And it also shows that, so it gives a criterion for whether or not a manifold is strongly parabolic. I won't worry about that. Okay, so what's the proof of the minimum principle? Well, what's the idea? So you take this positive superharmonic function, and then you flow in the direction of greatest decrease, or in the direction opposite to the gradient. And this flow is volume non-decreasing, because the divergence of that flow is positive. And on the other hand, since it's positive, it can't just keep running along super fast, because it can never get below 0, which means it's got to slow down to a crawl. And you can make that into an inequality if you want, but it's going to move more and more slowly. So suppose you start at some point, and you look what this flow line does. Well, you're going to sort of go in the direction of greatest decrease. Suppose it starts going out this convex core end. So if you flow in the direction of greatest decrease, and you always go out through the boundary of the convex core, wherever you start, the value of function is smaller at some point on the boundary of the convex core, and you win. But could this flow go escaping out the geometrically finite end? Well, the problem is that if you look at these surfaces, and you look at the neighborhood of radius 1s of these surfaces, well, these have bounded volume. So they're sort of narrows, right? I mean, your manifold is somehow supposed to not, I mean, your flow is supposed to move more and more slowly, but yet not decrease the volume. So imagine instead of a flow line, this was a little ball, and this little ball kept going out. But now if you look at that little ball, if you got this narrow, if you go further and further out here, it's taking it longer and longer to get through the narrows. But which means that there's a billion, if you get out to a step here, there's a billion balls inside the narrows. But that narrows has bounded volume. It can't contain a billion balls. It can only contain 100 balls. So that says that if you have any positive measure set inside the convex core where the flow goes out the end, you're going to run into trouble. It's sort of forced to turn around almost all the time and go back out through the boundary. So that means it has to, since this is the flow in the direction of greatest decrease, that means it has to achieve its infimum on the boundary. Okay. Right, so I think I would probably have to fill in more details about what kinds of surfaces I use. If you pick any specific kind of surfaces, you're okay. So Thurston used pleated surfaces, and you just make a little argument that the neighborhood of radius 1 of a pleated surface has bounded volume.
Controlled by the area.
Yeah, controlled by the area. It's a function of the area. It's a function of the genus. So these are all the same. These are all surfaces of exactly the same genus.
Since the hyperbolic area is controlled.
Yeah.
Zooming out these.
The area is controlled, and so you expect the volume to be controlled. Yeah.
So the bond from above from the volume like this? The volume is bounded from above.
Yeah, that's what you need. So I mean, it's a little lemma.
You need a lot of discrete surfaces to
Yeah, well, you need whatever. So you can use pleated surfaces. I like to use simplicial hyperbolic surfaces. Yair in his thesis showed you could use harmonic surfaces if you wanted to. So you have to pick whatever surface you like. You actually make this definition more precise by choosing some type of surface, and then you have to prove a neighborhood of radius 1 of that type of surface. Just the curvature bound tells you the area surfaces of the surfaces bounded from above. And so once you have the area of the surface bounded from above, you really expect the volume of its one neighborhood to be bounded from above. That's the whole idea. Yeah.
I missed the part where you get a million disjoint balls.
Well, the point is that it's slowing down. Its speed is going to 0. Because if its speed, if you start and the value of the function is 3, and your gradient stays, size 1, then if you travel 1 million miles, you're at negative a million. Well, negative 999,997, right? So because you start at 3 and you know you can't get below 0, all you can do is your gradient must keep getting smaller and smaller and smaller, which means your flow has got to slow down. Because the norm of the gradient is the speed of the flow. Okay. It's okay if I move on? Okay. Yeah, so that is now the whole proof of Allforce measure conjecture for topologically tame things. And you can also, another natural dynamical thing you associate to a manifold is its geodesic flow. And you might ask yourself, is the geodesic flow ergodic? Which means, are there flow invariant subsets of, is every flow invariant subset either of zero measure or full measure? And Dennis proved the geodesic flow of a hyperbolic 3 manifold is ergodic if and only if it admits a positive Green's function. So a positive Green's function has what? Oh, I don't think I said it right. You're right. I typed it right though. Do I get partial credit, Professor? You can see from the work that I really meant to say the right thing.
Another funny story here. This was proven by Eberhard in 1939, and an equivalent statement in the 60s was called Suji's problem.
Oh, really?
And I proved it in the 80s, but anyway.
How many flow lines of the brain actually exit the simple degenerate?
Instead of measure zero.
But many, or there's a range of them?
I don't know.
You mentioned one.
What? Do you know something about this? Okay, I can talk about it.
Was it?
I think it's probably dimension one.
So a positive Green's function, it's like a harmonic function, but it has a pole. So you can either sort of like, cap off the pole and make a positive superharmonic function, or you could work with the Green's function directly and show that if the limit set is the entire Riemann sphere, that there's nowhere for the flow to go again. You can still, if you have a pole, you can still flow backwards along the gradient at every point except the pole and make the whole argument work. So you see here that the geodesic flow of a topologically tame hyperbolic 3 manifold is ergodic if and only if the limit sets the Riemann sphere. Just a sort of very nice, simple criterion for ergodicity that you sort of what you expect. Okay, so now I was asked to do Hausdorff dimension, so I had to remind myself things about this, which I worked on it 20 years ago, but haven't thought about it a lot lately. But so let's let d gamma be the Hausdorff dimension of the limit set, and let lambda naught be the bottom of the spectrum of the Laplacian. So that's the infimum of the spectrum of, and my Laplacian is negative div grad. I mean, there's always this confusion with is it div grad or negative div grad. Patterson and Sullivan proved that if you're convex co-compact, there's this beautiful relationship that the bottom of the spectrum of Laplacian is exactly the Hausdorff dimension times 2 minus the Hausdorff dimension, unless the Hausdorff dimension is too small. It's less than 1, and if it's less than 1, it's just a Schottky group, which is that picture I drew with here's a circle, here's a circle, here's a circle, here's a circle, boom, boom. And maybe you have to have quasi-circles instead of circles. Okay? So let me just say something entirely too brief about what are some of the ideas that go into this. Well, first of all, you look at something called the Poincare series, which is you sum up e to the negative s, distance 0 to gamma 0. You just choose some origin in H3, and you sum that over the group. And the critical exponent says that when S is big enough, this converges. When S is 0, this doesn't converge. So there's some critical exponent, which is the barrier between convergence and divergence. Okay? And then you use that critical exponent and this series to cook up a measure supported on the limit set, which is called the Patterson-Sullivan measure. Basically, you take you take S bigger than the critical exponent, and then you take a point mass at each of the orbit points, and then you divide that by a term to make it converge. What? You divide it by the whole sum and it converge. And the key point about this, then you pass to a limit where s goes to the critical exponent, and if you assume that it diverges to the critical exponent, which it does for convex co-compact things, this all works and gives you a nice measure. And if it doesn't diverge, then you have to fuss around a bit. But the key thing about this is it transforms just like delta dimensional Hausdorff dimension under the group. So it gives you a measure, or really more a class of measures. Maybe think if we wanted to use the word conformal density, it transforms like delta dimensional Hausdorff to measure. And then Dennis used this to prove that, in fact, it is a multiple of delta dimensional Hausdorff measure. Okay, so this tells you that the Hausdorff dimension is the critical exponent. And then you can take this measure, and we saw that given some subset of the sphere at infinity, we constructed a harmonic function. Now you do the same thing. You take some subset of the sphere, in some d-dimensional subset of the Hausdorff of the sphere at infinity, which is invariant under the group, and you can integrate the Poisson kernel instead of to the power 2 to the power d, and look at the quotient, and that gives you an eigenfunction of the Laplacian, and with the eigenvalue delta 2 minus delta, because you're integrating an eigenfunction of Laplacian with eigenvalue delta 2 minus delta against some measure. So this is very, very loosey-goosey. Any experts want to tell me? Was there anything too bad about that? That's the basic idea, and then you have to check that this gives you an actual L2 function. There's various things to check here. Well, lots of things to check. I mean, it's a whole theory. And one thing that comes out of this theory is that if gamma is convex co-compact, the Hausdorff dimension is less than 2. Tukey also had a proof of that, and Dennis, in parallel, has a proof that the Julia set of a hyperbolic rational map has dimension less than 2. Now, Bishop and Jones showed sort of, there's a nice dichotomy that if the group is finally generated and geometrically infinite, then the critical exponent is 2. And sort of the amazing thing about this is that they didn't use tameness. they just did it. So none of this topological nonsense. On the other side, if you're topologically tame, but you're not geometrically finite, then lambda naught is 0. And so if you know what these words mean, if you take a surface here and a surface way out there, that they bound a submanifold with very big volume and very small area boundary. So the Cheeger constant is getting very close to 0, arbitrarily close to 0, so lambda naught goes to 0. That's the whole proof. And so you put these two results together, then in fact this relationship observed by Patterson and Sullivan in the geometrically finite case holds in general for a finitely generated Kleinian group. And since we know the tameness conjecture, you don't need that topologically tame assumption there.
Okay.
But it's always the Hausdorff function? D of gamma is the Hausdorff function?
Yeah.
Or is it critical exponent?
Well, that's another thing that follows from Bishop and Jones' result, that they're the same. Yeah.
Well, I mean, the left hand side, it's always equal to that. It's
Yeah.
less than 1.
If it's less than 1, it's still a Schottky group. Yeah.
It has to be shown.
Yeah. And if it's equal to 1, it could also be a Fuchsian group.
What?
Well, if it's equal to B1, if it's equal to 1, there's also some funny things that happen exactly at 1, right? And then you have to either be Schottky or Fuchsian. Okay. And another thing, you can show that the volume of the convex core controls the Hausdorff dimension of the limit set. And so there's some expression there which I think I got right. I'm not guaranteeing you. But the moral of basically it's bounded by in between the reciprocal of the volume of the convex core and the reciprocal of the square of the volume of the convex core, the difference of the Hausdorff dimension to 2. And so this makes explicit the thing you obviously think, that if your limit set was fuzzy, your convex core would be thick. Right? So, and this, the same thing holds sort of trivially if you're geometrically infinite. Well, the one has an exponent of 2. I'm not sure actually whether it should be like volume of convex core squared or the reciprocal of the volume of the convex core. Do you have a guess, Chris?
What? I'm not sure. I have to think about it.
Okay.
Well, actually, I had thought about it, but I've forgotten the answer. I can think about it again.
Okay. So that's sort of my take on the Hausdorff dimension applications. Let me mention a purely topological application, which is there's a conjecture of Simon's, which says that if you have a yeah. Well, it's yeah. There's actually a similar theorem to this due to Shane and someone I know anyway. But this is closely related to the theorem that for a closed hyperbolic 3-manifold, lambda 1 lies between the reciprocal of the volume of the manifold and the reciprocal of the volume of the manifold squared. So there is an analogous sort of thing for closed things. Yeah, for closed things it's true. I see. Volume of the convex core isn't really the right thing. But notice there's an Euler characteristic to the boundary term there. So in there too, which I didn't really talk about. That's sort of, I think, where you're seeing this actually come. Okay. So there's an old topological conjecture of Simon. He said if you start with a compact, irreducible 3-manifold with boundary, and you pass to some cover of it, and that cover has finely generated fundamental group, it should still be topologically tame. And I like to use this as an example of sort of the power of hyperbolic geometry, right? Because, back in the 70s, they were working on this kind of hard, and they could show it for in some cases, they could show it for cyclic groups, and in some cases, they could show it for the boundary subgroup. And I think maybe there's some other proof for Z plus Z subgroups. But it was really hard work and not much progress. But it turns out that if you take Thurston's geometrization theorem, you can prove large cases of this totally trivially. It's kind of a cool thing. I don't really have enough time to say much about it. But if you take a convex co-compact hyperbolic 3-manifold, it's not at all hard to show that any cover of it with finely generated fundamental group is also convex co-compact. That's really very easy to do using geometric methods. It's a one-line proof if I did it for you. And that's a very strong tameness result. But if you combine the tameness theorem and the Thurston's geometrization conjecture, some of the original work of Simon, and an argument of Long and Reed for handling some of the ciphered fibers special cases, this gives a full proof of Simon's conjecture as a consequence of Marden's tameness conjecture. No, this is, I don't need boundary there. I don't need boundary. If it does, that's why instead of talking about N being topologically tame, M could have boundary or could not. That's why I have to talk about the interior of N being topologically tame when I'm being careful. Okay, there's also some group theoretic applications. A lot of these come down to the fact that if you take a closed hyperbolic 3-manifold, it's a consequence of the covering theorem of Thurston, and if I extend it a little bit, that if you take any cover of a closed hyperbolic manifold with finely generated fundamental group, it's either convex co-compact or it's exactly this picture. Right. Did I erase it? No. Here's a closed hyperbolic 3-manifold. Here's a cover which is not convex co-compact. So up to finite index, Either your cover is convex co-compact or it's this picture. And this turns out to be a very powerful tool in sort of understanding the group theory of Kleinian groups. So as one example, combines work of the covering theorem and some work of Harry Susskind, shows that a closed hyperbolic three-manifold has the finitely generated intersection property if and only if it does not have a finite cover which fibers over the circle. And of course, now there's been a lot of progress pointing to the question of Thurston's, which maybe every closed hyperbolic three-manifold does have a finite cover fibering over the circle. But this is sort of a group theoretic criterion for that. There's also some applications to separability properties. For instance, Eagle-Long and Reed show that every geometrically finite subgroup of a Bianchi group is separable. Well, now you can use this. You can erase the geometrically finite assumption. And there's also applications to the pronormal topology. So here's, for example, a cool one due to Glossner, Soto, and Storm, which is sort of related to a question of Margulis and Seufer that they actually asked about PSLNZ. But it says that if you have a closed hyperbolic three-manifold and you have a maximal subgroup, which means if you add in any more elements, it immediately becomes the entire group. Then either it's finite index, obviously any index 2 subgroup will do, right? Or if it's not finite index, it's infinitely generated. So they asked if this was true for I think PSLNZ, if I remember right. There's some interesting things. And one thing I wanted to do, just to give a little setup, in case Ken wanted to mention the ending lamination conjecture, let me just, I have 4 minutes, right? Excellent, okay. I can state the ending lamination conjecture a little more carefully in 4 minutes. I know this is a radical left turn, but we sort of now have the technology. So first of all, to do this, you need something called the curve complex, which hopefully a lot of people have seen. And it's sort of a natural object associated to a surface. You first of all take the collection of all simple closed curves, or really isotopy classes of simple closed curves, on a surface, and you make them the vertices of a complex. And then you join two vertices by an edge if the curves are disjoint. And then you join, 3 vertices, you span them by a triangle if all 3 of the curves are disjoint, etc. Go up in dimension. This was first study introduced by Harvey and was used extensively by Hare on his work on cohomology of mapping class groups. And Mazer-Minsky sort of made this a really strong geometric tool by proving that it's a Gromov hyperbolic metric space. And then work of Klareich shows that its Gromov boundary can be identified with the space of filling geodesic laminations on the manifold, which just mumble about that a bit, okay? So now, if you have this sequence of hyperbolic surfaces going out your geometrically finite end, well, on this surface, it's a hyperbolic surface, and its curvature less than -1, therefore its injectivity, its area can't be too big, so its injectivity radius can't be too big, so there must be a curve of some uniformly bounded length. This is an observation of Baer, it goes back to Baer's. So I can always, on each of these surfaces, I can pick out, here's beta 1, some curve of bounded length on this surface, beta 2, beta 3, I get a sequence of curves. That gives me a sequence of vertices in the curve complex, and you can define something called the ending lamination of the end, which you take those sequence of vertices, and they go off to infinity in the curve complex, so they converge to some point in the Gromov boundary. And that point they converge to in the Gromov boundary is called the ending lamination. So even if you don't know what a lamination is, you can just think of it as a point in the Gromov boundary of the curve complex. And of course, there's a fair amount of work to show that's a well-defined point, right? I mean, there's a lot of choices involved in this. But in fact, however you do this, whatever choice you make, you always get the same point in the Gromov boundary of the curve complex. And the conjecture is that, remember we saw in the convex co-compact case, we would cap off that convex co-compact end with a conformal boundary component, and that conformal structure on that boundary surface was all we needed to determine what happened inside. And so the ending lamination conjecture says, well, Okay, maybe this end is also capped off. So if I tell you that end's capped off by this surface, this end's capped off by that surface, and this end has this ending invariant, that's enough information to reconstruct it. This is, again, something, I don't know how he guessed that that was enough information. I mean, you seem like you've thrown away an absurd amount of information. You've just taken, first of all, you have these surfaces going out, you pick one curve on the surface, you pick some limit. I mean, first of all, seeing that limit should be well-defined is kind of surprising. And even once you've seen it's well-defined, it's really sort of a leap of insight to guess that that should be enough to determine. But that's what he did, and he was right. So the ending lamination projects that a hyperbolic 3 manifold is determined, well, up to isometry, first of all, by its homeomorphism type, and then secondly, by its conformal boundary and the ending lamination. So together, the conformal boundary and these ending laminations are called the ending invariants. So we think of sort of, again, there's sort of like in the Mandelbrot set, you have combinatorial data, and then you have analytic data. And so here we have topological data and analytic data. So that's sort of the analogy.
How do you give the information?
Well, so one thing, here's one way to formalize it. First of all, in the manifold, I'd say I can find a compact core in the manifold, and on that compact core, associated to every geometrically finite end, I have a conformal structure, and associated to every geometrically infinite end, I have this lamination. And then if you have a homeomorphism, if you have two manifolds, and you have a homeomorphism between their compact cores, which takes conformal structures to conformal structures and ending laminations to ending laminations, then that homeomorphism is homotopic to an isometry. That would be one precise way to state it. Yeah.
Instead of ending laminations on one thing, is that some kind of a reasonable space? Space?
Well, it's a space. Yeah, you can put a topology on it. Yeah, one thing I would say is that what's true is that the ending invariant data in any reasonable topology you put on the space, on any reasonable topology you put on the space of ending invariants, they vary discontinuously. So you can put a topology on those spaces, but it doesn't really capture their topology if you sit them inside the character of writing. If you don't capture the topology of AH of M within the character of writing. So this is something that's totally different for hyperbolic, for Kleinian groups. We have nothing like in the MLC case, you have something called the abstract Mandelbrot set, which is a complete parameterization, conjectural parameterization of the Mandelbrot set. We don't even have a conjectural parameterization in terms of these invariants. Because remember I said yesterday the homeomorphism type isn't continuous with respect to the topology on the space representations, and neither are these ending invariants. And I'm beginning to. I hope so, but the spaces. How do you so we're going to talk about this more tomorrow, but the space isn't locally connected. So coming up from a parameterization for a space which isn't locally connected is it's going to be messy. Whatever it is, it's not going to be nice. And so, I think probably this is true of deformation spaces of rational maps in higher dimensions as well. Right? The Mandelbrot set is a one complex dimensional deformation space. And it's true, if you have a one complex dimensional space of Kleinian groups, you can't always parameterize them. The only real cases occur with things like the Bears slice and the Mascot slice of the puncture torus groups. These are one-dimensional, and they are, you can parameterize their boundaries. The boundaries are Jordan curves, and the data is all continuous. But once you go up into higher dimensional deformation spaces, all the data stops being continuous. Does the same thing happen in rational maps? Anything equivalent?
Since Jack is sitting behind me, I'd say he has a beautiful picture in one of his papers of the real slice through the cubic polynomials, and it has this terrible non-locally connected behavior. So I think that what we think is true for the Mandelbrot set is an artifact of being in dimension 1.
Right. Okay, so so Yair and then Yair and Jeff and I proved the ending lamination conjecture for topologically tame hyperbolic 3 manifolds. You combine that with the tameness conjecture, and you get Thurston's ending lamination conjecture for everything. And I'm 4 minutes over, so I better stop. Sorry. Well, for closed manifolds, it's easy because you eliminate the word homeomorphic. It's just for the. Well, yeah, because for instance, Yair first, because they have bounded geometry. So Yair proved ending lamination conjecture in the bounded geometry case long before the general case, and you have all this compactness around, so it makes it easier to prove everything.
I'm wondering what was motivation example for asserted. We could have some very simple motivation example.
Yeah.
I know what the picture was in those days. There was the Jorgensen example of the function torus, and gave a geometric model of what the end looks like in terms of continued fraction expansion of the eigenvalues of the element of SL2Z that describes.
Oh, that makes sense. Yeah.
So the idea of this was you just need data that will give you enough data to give you a model, approximate model of the bounded distortion of what the end looks like. You have these Peter surfaces going out. So something like a continued fraction, Peter surface going out, something like a continued fraction expansion of the ending lamination. So you have to make a model. And I think that's finally what maybe was done.
Yeah.
But that's the reason for GFC. And then if you have an approximate picture, then you get a Bilet-Fitts map between any two examples, and then you use the usual ergodicity rigidity results to finish it off.
That's how the proof goes. Yeah, you don't have to talk tomorrow.
No, you have to take the ball.
Yeah. Yeah, there was a little bit of work in that.
Yeah.
No, yeah, that's true. That's exactly how the proof goes.
I guess in this case it is like stable and unstable correlation for the pseudo-North matter of this and something like that.
Right, it's exactly
so the question whether they appropriate somehow I can guess that they determine the pseudo-North matter set, so you know the stable and unstable correlations.
Right, but but why would you, so the thing is, why would you suspect that if you had something which had the right ending laminations, it was a cover of something fiber with a circle? That's the hard, right? Yeah. So, but yeah, so you got to try to build some sort of, use that data to build some sort of model, and yeah.
Okay, so why don't we break for, why don't we thank the speaker again? Yes.